Welcome to this episode. It's about chapter 15 of this special publication of SAG. In this study by McFall and colleagues, they bring some important and unique contributions to our understanding of porphyry copper deposits, especially regarding their precious and critical metal byproducts. First, it makes a direct comparison between subduction-related and post-subduction porphyry systems. They have used three case studies or three global scale types of porphyry deposits: El Teniente in Chile, Murat Dere in Turkey, and Scories in Greece. And what is fascinating is that it shows that metal enrichment, particularly for gold, PGE, tellurium, and bismuth, they're not strictly controlled by tectonic setting. And one of the most important findings is that the Scories stands out among these deposits. It's quite enriched in palladium, platinum, bismuth, and tellurium, and it's suggesting that semi-metal melts like bismuth and tellurium, and they could be acting as critical vectors for transporting and concentrating PGE. And this mechanism hadn't been already shown or clearly shown in porphyry systems before. This study also finds that most gold and PGE are not actually in the major sulfide minerals like chalcopyrite or bornite. They're mostly hosted by accessory phases like electrum, marlinskite, or other telluride minerals. And that's a huge information for geometallurgical and metallurgical planning and metal recovery strategies. On the method side, this study is just as impressive. They've used whole rock assays to get a handle on total metal contents. Then they've used in situ laser ablation, ICP-MS, to directly analyze trace elements in individual sulfide grains. And important thing is that they've used a bunch of different kind of sulfide minerals. They're not just focused on pyrite or just one or two sulfide minerals. They analyze pyrite, chalcopyrite, bornite, molybdenite, galena, and sphalerite. And this was paired with SEM-EDS screening to make sure that micro-inclusions didn't affect the results. Another strength of this study is a global comparative approach. They built a sulfide trace element database for more than 1,000 entries from 21 porphyry deposits worldwide. And this let them position these case studies and this study in a global context. And finally, they performed mass balance calculations to estimate how much of each metal is in sulfides versus accessory minerals, and back that up with robust non-parametric coloration statistics. So it's based on strong statistical methods. Altogether, this chapter doesn't just map metal distributions, it changes how we think about how these metals behave, move, and finally concentrate in porphyry systems. This figure provides the regional tectonic context for these three porphyry copper deposits. which have been analyzed in this study. On the left, in panel B, we see El Teniente in central Chile. This is a classic subduction-related deposit formed in the late Miocene-Pliocene porphyry belt along the Nazca plate subduction zone. The flat slab segment just east of the deposit is significant as it influences magma generation and volatile transport in the crust. Moving to panel C, the map shows the Scories deposit in northern Greece. It's situated in the Serbo-Macedonian metallogenic province near the Rhodope metamorphic core, and this is a post-subduction system where exhumation and crustal extension led to magmatic activity during the Miocene. This setting is key to its enrichments in palladium, platinum, and bismuth. And on the right, in panel D, we see the Murat Dere in western Turkey. It's hosted in the North Anatolian belt, which is another post-subduction environment. It formed in the Eocene after crustal thickening and exhumation. The region is part of the larger Tethyan metallogenic belt. What's important here is that the tectonic settings differ significantly from each other, and this lets the authors isolate whether metal enrichments like gold, PG, or tellurium depend on tectonic setting or other magmatic and hydrothermal processes. Also note the symbols in these figures. We have blue X's, which indicate other porphyry deposits from the global sulfide trace element database, and we have red X's, which show the deposits that were directly sampled and studied in this research. In this slide, we have metal concentrations in sulfides. This figure shows box plots of trace metals. We have gold, silver, tellurium, selenium, and bismuth in 4 key sulfide minerals: pyrite, chalcopyrite, molybdenite, and bornite. And the colors are important. Green is the El Teniente, blue is for Murat Dere, orange is Scories. Also post-subduction, but unusually platinum PG rich, and the yellow represents global porphyry averages. Starting with pyrite in the top left panel, Scories pyrite really stands out with high tellurium and bismuth, which are much higher than the global norms. Murat Dere pyrite is also surprisingly rich in selenium and bismuth, which supports the idea that post-subduction systems tap deep reservoirs enriched in these chalcophile elements. In chalcopyrite, shown top right, all 3 deposits show relatively low gold, but Scories again stands out for elevated selenium and bismuth. And El Teniente, on the other hand, is depleted in bismuth, exactly what we expect from a more typical copper molybdenum porphyry without unusual precious metal enrichment. Looking at molybdenite in the bottom left, Murat Dere and the Scories both show higher selenium content compared to the global trend. Gold and bismuth values, though, are scattered, which likely reflects tiny inclusions rather than being part of molybdenite's crystal lattice. And the most important and interesting result comes from bornite, bottom right. At scories, bornite is extremely enriched in bismuth and tellurium, reaching some of the highest levels across all the datasets. This makes sense because scories is known for hosting PG-bearing accessory minerals like marinskite and subkate. In contrast, El Teniente's bornite carries higher silver but not bismuth or tellurium. It shows a very different metallogenic signature. So the big takeaway here is classic subduction porphyries like El Teniente follow predictable metal distribution patterns, but post-subduction systems like scories and Moratere, they show anomalous enrichments in bismuth, tellurium, and selenium, and in the case of scories, even PG associations. These differences point to contrasting tectonic setting, oxidation states, and fluid evolution passes, which gives us a more complex picture of how metals are sourced and partitioned in porphyry systems. This figure presents a global comparison of trace element concentrations in sulfide minerals from subduction related or SR and post-subduction PS porphyry systems. These box plots break down the distribution of 5 key elements: gold, silver, selenium, tellurium, and bismuth across sulfide types like bornite, chalcopyrite, molybdenite, pyrite, and galena. So let's go panel by panel, starting with panel A, gold. Gold is generally low across all sulfide types, regardless of tectonic setting. But interestingly, galena shows relatively high gold concentrations, which is a non-traditional host mineral. This likely reflects micro-inclusions of electrum or native gold rather than solid solution. In panel B, silver, the standout again is post-subduction galena with very high silver content, suggesting silver solid solutions or silver-rich tellurides. Bornite in both SR and PS settings also shows elevated silver, aligning with prior studies that note silver's preference for copper-rich sulfides like bornite. Panel C shows selenium, and this is where we start to see tectonic control. Post-subduction molybdenite and chalcopyrite exhibit some of the highest selenium concentrations. Indicates that these systems tap into deep selenium-rich sulfide resources, likely cumulate derived. Pyrite shows a wide range, but generally less selenium in subduction-related deposits. Moving to panel D, tellurium, there is no strong tectonic bias, but the variation is notable. Tellurium concentrations are broadly higher in molybdenite and pyrite, again often tied to accessory telluride mineral inclusions. What is particularly interesting is that pyrite from post-subduction settings shows a wider and higher tellurium range, possibly due to late-stage hydrothermal fluids. And finally, in panel E, bismuth, we see one of the clearest contrasts. Post-subduction bornite and molybdenite are heavily enriched in bismuth, some reaching over 1000 ppm. This suggests bismuth behaves like a collector metal in these systems and possibly mobilized in semi-metal melts. Again, galena stands out with relatively high bismuth, despite being a minor sulfide phase. So, what is the broader message here? While subduction-related porphyries show more consistent and more moderate metal distributions, post-subduction systems, on the other hand, exhibit highly variable and sometimes extreme enrichments, particularly in bismuth, selenium, and sulfur, and then silver. These enrichments are strongly linked to mineral hosts like bornite and molybdenite, which may concentrate these elements via inclusion mechanisms or fluid evolution in deep crustal settings. Overall, this figure supports the idea that tectonic setting shapes metal budget potential, but mineralogical pathways and fluid chemistry ultimately control metal's residence. Here we have mantle normalized profiles and PG trends. This figure dives into the trace element fingerprints of porphyry systems, showing us how precious metals and PGs behave in different tectonic settings. Starting with mantle normalized profiles in panels A through D. Panel A, El Teniente in green, looks like textbook subduction related copper molybdenum porphyry. The profile is flat with low PGs and only modest gold and tellurium. Exactly what you would expect from a deep crustal source without much volatile overprint. Panel B, Moratere in blue, is already different. The curve slopes upward with enrichment in palladium, platinum, gold, tellurium, and copper. This kind of profile suggests late-stage fluids or semi-metal melts, adding extra metals, which is a hallmark of post-subduction systems. Panel C, scories in orange, is where things get dramatic. Its profile spikes sharply in tellurium and PGs, way above mantle values, and that's a strong evidence for bismuth tellurium rich metals melts or oxidized magmas acting as collectors for PGs, and it's something which is very unusual in porphyry systems. Panel D overlaps other PG-rich porphyries like elastite, kalmakir, and BC porphyries. They show similar upward sloping patterns, reinforcing the idea that alkaline or post-subduction magmatism plays a key role in concentrating rare metals. And now the box plots. Panel E shows total PPGE, palladium, platinum, and rhodium. Scories and elastite are off the charts compared to subduction-related deposits, confirming that post-subduction systems are uniquely PG-rich. And panel F shows whole rock gold again. Scories and Moratere dominate, while El Teniente lags behind, despite being a copper giant. The most revealing panel is G, the palladium platinum versus palladium iridium biplot. Scories and Moratere separate cleanly from El Teniente and other arc-related systems. That means they follow the different evolutionary paths, with more oxidized volatile-rich magmas and likely the involvement of bismuth tellurium melts, acting as metal concentrators. And the big picture is this: PG and gold enrichment is not random. It reflects tectonic setting, magma chemistry, fluid evolution, and even exotic processes like melt immiscibility. Scories in particular pushes the boundaries of what a porphyry can be, and blurring the line between porphyry copper deposits and magmatic PG systems. To wrap up, this study challenges the traditional view that tectonic settings alone controls pressures and critical metal enrichment in porphyry systems, while subduction-related systems like L10 are known for their copper molybdenum endowment. We see that post-subduction deposits like scories and moratorium can actually show even higher enrichment in gold, PGs, bismuth, and tellurium. One of the key findings is that these metals are mostly hosted in accessory minerals, not the major sulfides, and that has big implications for resource estimation and metallurgical recovery. The role of bismuth tellurium-rich semimetal melts as potential transport vectors for PGEs is particularly interesting, and it opens up a new exploration model for PG-enriched porphyries, especially in alkaline and post-collisional settings. And also geochemical ratios like palladium to platinum and palladium to iridium, as well as Manter-normalized multi-element profiles, proved useful in distinguishing high fertility systems. Overall, this study shows that to understand and predict porphyry fertility, we need to look beyond tectonic and integrate mineral chemistry with fluid evolution and melt dynamics into an exploration toolkit. Thanks for watching.